Hello and welcome everyone to today's webinar on subwatershed-based lake and river routing products for hydrologic and land surface models applied over Canada. This is the fourth in our Lake Futures webinar series and the first session back in September. My name is Kirsten Grant and I'm the project coordinator for Lake Futures, which is based out of the University of Waterloo. But like many of you here, I am joining you from my home today. I want to start by acknowledging that here we are participating on the traditional territories of the First Peoples across this country. Here in Kitchener-Waterloo, I acknowledge that I'm on the Haldimand Tract, land that was promised to the Haudenosaunee peoples of the Six Nations of the Grand River. The Haldimand Tract is within the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. I would also encourage you to take a moment to recognize the traditional land where you are. Brian, if you could move to the next slide.
Okay.
So today's event is being hosted by Lake Futures, which is based at the University of Waterloo and led by Dr. Nandita Basu, who we've heard from a few weeks ago. The project involves over 20 researchers from 4 universities and is a 7-year-long multidisciplinary project. The goals of this project are to deliver adaptive watershed and lake management solutions that minimize trade-offs between lake ecosystems, water uses, and economic growth. As we finish up year 3 of the project, we decided to create this webinar series to connect our findings with external practitioners and other researchers. And the goals of this series is to share our latest research, discuss the implications of this research and how it might inform water policies and programs, and to promote dialogue between researchers, partners, and stakeholders to help us inform the next phase of our research project. Lake Futures is a project under the Global Water Futures Program, which is the world's largest university-led water research program, with the goal of delivering risk management solutions for managing water in Canada and other cold regions, informed by leading-edge water science. So next slide, Brian. We will get to some quick housekeeping logistics for today's webinar. So we'd ask that you please use the Q&A feature to post questions and feel free to do that as the presentation goes on. And we will get to those in our Q&A session at the end. Please use the chat box to share any general comments or ideas and engage in dialogue with other participants. This webinar will also be recorded for viewing later. So for today's format, we'll begin with a presentation from Dr. Bryan Tolson, followed by a Q&A. We're hoping for this to be a two-way conversation, but recognize that this can be a challenge in this format. So as the presentation goes on, we would encourage you to share your thoughts in the chat box. To help us gauge our audience today, we'll start with a quick poll of those joining our webinar today. So I will ask you which best represents your organization: government, non-government, academic institution, industry or consulting, or maybe you're in another category that we missed. We'll leave this up for a few moments to give you a minute to respond. So that's great. We've got a lot of folks from government and academic institutions joining us today. It's nice to have a mix of interests, so we're glad to have you join us. So without further ado, I would like to introduce today's speaker. Dr. Bryan Tolson is a professor in civil and environmental engineering at the University of Waterloo. His expertise is in hydrological modeling, model calibration, sensitivity and uncertainty analysis, and optimization of water resource systems. So Brian, take it from here.
Thanks for the introduction, Kirsten, and thanks for everybody who wants to spend part of their afternoon with me. I hope you learned something from this talk. I have a start with a number of co-authors and collaborators on this work. I've been working on this project with Ming. Ming Han is a PhD student at the University of Waterloo. He started this work about 3 years ago, and all of the co-authors and I and James Craig in particular have been working on this for about 3 years, the first 3 years of the Lake Futures project, and we continue to work on this. So Ming and I basically developed the presentation, so I thought I'd highlight that. In terms of this talk, I'm going to tell you about our national routing products. I'm going to tell you about some hydrologic routing software we're using, and I'm going to tell you about a GIS routing toolbox that we're developing today. And I think that these are useful in applications that you might be involved in or that require things like knowing the topology or connectivity of a lake or river network, knowing channel characteristics like slope and roughness, knowing lake characteristics like area, volume, or outlet description of the lake. It would be useful, I think, if you're going to be building a new hydrologic or water quality model. For example, where you had to make discretization decisions associated with your watershed. I also think that it would be useful even if you're already modeling, if there's an existing modeling study of hydrology or water quality that you're working on. In particular, you'd be able to use probably the routing tool that we have and the methodology we have to route model fluxes through a complex lake and river routing network. So hopefully most of you would fall into one of those categories as a potential user, but I think there's lots of other reasons to stick around and listen as well. So some motivations first for this work. The main motivation for this work is that we wanted to not allow modelers to continue to ignore lakes in hydrologic modeling applications. By and large, all hydrologic applications in Canada typically do not explicitly simulate or represent lakes in their model, except for the really large lakes. But most modeling studies ignore modest or moderate size to small lakes. And that's unfortunate because we actually know that these lakes exist and we typically know exactly where they are, especially now with the relatively new HydroLakes global database showing all lakes in the globe that are greater than 10 hectares. If you're a hydrologic modeler or a watershed modeler, you know that we have a ton of unknowns when we build these models. And so I find it funny that one of the things that we can know with near certainty is where and how big these lakes are, but often we don't include that information in some of the models that we build. And that doesn't seem like an appropriate way to go. And so that's why we wanted to embark on this research to build these routing networks. Of course, this is really important in Canada, right? 10% of Canada is covered by lakes, and 900,000 lakes exist in Canada according to HydroLakes that are greater than 10 hectares. And I think we all know that lakes control timing and volume of discharge, and as well as define watershed connectivity or contributing area. And so they're really important to try to represent in the models that we build to talk about streamflow or water quality impacts. Another motivation is, from a research perspective, is we wanted to objectively assess which lakes we can ignore in hydrologic modeling applications. Now, this recognizes that there's going to be applications where maybe we don't want to explicitly simulate water levels and inflows and outflows for 10,000 lakes. That could become a computational burden, and so that might not be necessary for all case studies. Unfortunately, if you look through the literature, it's typical to have basically a subjective decision rule for including lakes in large hydrologic modeling applications. And so in some studies, you'll see that there's an arbitrary threshold of, we only consider lakes greater than 100 square kilometers, with the only evidence of 100 being a good choice, as it's a nice number to report. I think that, personally, I think we need to be very much less subjective when we build these models, if we want to build these models to better simulate flood forecasting and do better and be more reliable in climate change impact estimation. So that's another motivation. And finally, the last motivation for this work is that we really believe, our group really believes, that a vector-based rather than a gridded routing approach is needed if you're going to represent numerous lakes in your model. So the top figure here is just showing an example network that's a vector-based network, and a vector-based routing network essentially moves water across the landscape between irregular subbasins or catchments or subwatersheds, whatever you want to call them, and irregular lakes. And so each of these subbasins would be treated as a response unit, and things would cascade downstream. Now, gridded routing models, on the other hand, impose a regular grid on top of your stream and lake network. And in cases where you don't have a lot of lakes, sort of a gridded approach to routing might be reasonable. But as soon as you have really complex sets of lake networks that are not square, it can be really challenging to overlay lake shapes on a regular grid and come up with a flow path through these regular grids that make any sense. And so we think that it's much better to go vector-based. And so another motivation, then the related motivation here, is that the Environment Canada and Climate Change operational land surface routing model that they have makes forecasts with a gridded routing model. So they ignore most lakes in Canada except for the largest lakes. And so part of this work is supported now by Environment Canada, and we're trying to demonstrate the value of moving from a gridded routing framework to a vector-based routing framework. So with that, with the motivation, I think I can tell you now the overview of the rest of the talk. So first, I want to tell you about national scale lake and river routing products that we built. The second thing I want to talk about is the application of these projects. For an example, hydrologic routing application, and this is specifically using the Raven hydrologic modeling software in routing mode only. This would be so our paper on this was the first paper to demonstrate that. And then the last thing I want to give you an idea about what we're working on is this GIS lake and river routing toolbox. And essentially this toolbox is built so that it allows you to build customized routing products. So if you don't like the routing products that we've got that are pre-compiled, then this is a customized open source software that we're building so that you can build your own routing network. And so I'll talk about all three of those. So first is our national scale or pan-Canadian lake and river routing products. So the first thing that's worth noting is that the current, I would say the current national scale data sets available, like hydrosheds, hydrobasins, and hydrolakes, are insufficient for hydrologic routing, especially at a daily time step. They're a great start and they form the basis of what we're building, but they don't have things like river channel characteristics such as Manning's End. And most importantly, perhaps, they also don't have a sort of hydrologically consistent connectivity that I think is appropriate for routing for operational purposes. So for example, we've pulled the following example from hydrobasins. And so the first figure here is showing two subbasins. So we'll focus on this long subbasin here. This is the flow path that would be delineated with from the hydrobasins and hydrosheds work. And this is a lake that we might want to represent in the network. Well, hydrobasins provides a shapefile with inserted lakes. But what happens in that product that's distributed is there's an arbitrary split in the watershed along the flow path created, and the network topology here causes water from subbasin C1 to drain into artificial subbasin C2, which is on the right side of the river, and then that flows into the left side of the river, which is artificial subbasin C3, which then flows out of the subbasin. So there's this weird routing of water between the lakes and the subbasins that happens in hydrobasins that is hard to reconcile. And so we don't think that's the appropriate approach for operational routing purposes. And so that's why we need a different national scale data set for hydrologic routing. So these products are available right now on Zenodo. Obviously this presentation will be available after, so this link can be shared. Maybe somebody can put it in the chat. The methodology and overview of how we develop these lake and river routing products is described in the paper that we just published in the Canadian Water Resources Journal. And so here I just want to show you a little bit about the core methodology that we use. So when we generate these routing products, we start with the core information, which is the hydrosheds and hydrobasins products. And so, for example, hydrobasins gives you different levels of subbasin discretization across Canada based on the Hydrosheds DEM. And so these subbasins, for example, I think this is level 6 or level 7. This is like level 12. But the core attributes here are the routing topology, or which subbasins flow into which other subbasins, and then the subbasin areas. So that's the first component. The second component is in the hydrolakes product, which is just the polygons of all the lakes, and it describes each lake in terms of the lake area, volume, depth, and importantly, the pour point location, or where the lake empties. And then we also have to take land cover maps and Water Survey of Canada gauge station locations and a couple of other empirical studies. And we put that all together. We do a bunch of GIS processing, and then we've come up with 12 different pan-Canadian lake and river routing products. And so let me tell you a little bit about that processing. So here's an example watershed we have. So if we focus on this lake here, what happens in our logic of lake routing is that every lake outlet is defined as a subbasin or a catchment outlet. And then all lake inflow points, so for example, here, here, and here, essentially define the upstream subbasin outlet. When we do that, we also note that each lake has a corresponding lake subbasin. So this is the lake subbasin associated with this lake. And there is no channel in a lake subbasin. All the water that would be poured into this subbasin would be assumed to be delivered not in a channel to this lake, okay? But with hydrologic routing, anything upstream you can see in these channels would be simulated with some routing, hydrologic routing logic, and some delivered through the channels. The other thing that we do is we make sure that all the 6,300 Water Survey of Canada stream gauge locations are included in our products as subbasin outlets, which means that you can easily check the routed flows against measured flows, because the locations are consistent with one another. And then another key assumption is that for all the lakes we represent here, we make the extreme assumption that they all behave like a broad-crested weir. And so to parameterize the outflow from any lake, we need to know the crest width for the outflow, the natural outflow structure of the lake. And that crest width is essentially derived from the upstream drainage area based on some empirical equations that people have developed in the literature. Now, some more information about our GIS processing. So if we look at an example lake catchment, this is hydrobasins data at level 12 with the flow paths delineated and the corresponding subbasins in hydrobasins. And so what we do here is we then put on top of that the hydrolakes polygon. So there's the lake of interest that we include and the resulting subbasin network in our routing products. And so the key thing that you can see here is that when we include a lake in this, in the routing product, the lake has multiple inflow pour points. So these are all labeled by number 2. And then there's all these small areas around the perimeter of the lake that don't have a channel in it, but all the water that would be applied here would just be delivered to the lake. And so this is the outflow point. So that gives you a sense of what things look like when we're delineating our lake and river routing networks. I want to describe quickly a level 12 and all lakes product. So we basically combine, for example, hydrobasins level 12, which is the most detailed hydrobasins product available. Plus we put on all the lake polygons and hydrolakes on top of that. And when we combine those two things, we get a product that we call L12-Lake 0. This product covers Canada. It has a total of over 200,000 catchments in it. Each of those has an average area of about 60 square kilometers. And in that product is about 87,000 lakes. So one thing of note here is that there's a lot more lakes in hydrobasins than 87,000. And these lakes, we basically put all the lakes that are in hydrolakes into this product, except what ends up happening is for every subbasin, we have a flow path that's derived from hydrobasins, but not all the lakes actually are connected to that flow path. And so we made the decision in version 1 of our product so that any lake that's not actually connected to the flow path is not included in the routing products that we build. And that's a reasonable first assumption, because I think the majority of our non-connected lakes, if you will, are quite small. So so I just wanted to explain why this number was much less than the total number of lakes in the HydroLakes database. So that's an example product. We build 11 other routing products that are not quite as detailed. For example, using hydro basins level 7 through 11 discretizations. And then we also have a second set of routing products where we don't consider lakes that are less than 1 square kilometer in area, so that we have fewer lakes. And so what ends up happening is we have 12 different lake products, lake and river routing products, and you can see how many catchments they have, how many lakes are included in each product, and then the average catchment area, as well as the median lake area. So as soon as we start deleting lakes that are all less than 1 kilometer squared, that's the last 6 products here, we start getting the average or the median lake size being 2 or 3 kilometers squared. So not so small. And that obviously would be beneficial if you don't care about the tiny, tiny lakes. The attributes, I guess, is the core of what these products are. It's important to be clear about them. Each of these products is distributed as shapefiles. And so, for example, each of these products includes sort of the upstream and downstream subbasin ID so that you can know where things drain. The area, as well as the slopes of the river and the basin. We derive Manning's N coefficients for the overbank areas and the channel itself. We come up with a default or an initial characterization of the bank full width and depth of all the river channel segments across the country. We have a mean flow based on a regression equation. This is all, so when I say C 2.12, that's on our routing product paper if you want to go there to see the details of that. Of course, we grab all the hydro lakes and information, so lots of the lake information comes from hydro lakes. Then importantly, for each lake, we actually, from hydro lakes, we can tell you whether or not it's a natural lake or it's a reservoir or it's a natural lake with a regulation structure. Now, I'm not sure how reliable these characterizations are, but they're at least a first cut available nationally, I would say. And then we also tell people whether the subbasin outlet corresponds to a Water Survey of Canada station. So all of these parameters or all of these properties of the watershed and channels are needed if you want to perform any hydrologic routing with any model. So anybody who wants to do hydrologic routing should be able to download this information and convert the information into their specific modeling format and then make use of it. As I said, these are national scale products. They're a first cut estimate. And so users should always be checking the product attribute values against any local knowledge or data they have. And they'll want to update their case study specific routing inputs as needed as that's appropriate. So now it's time to move on to an example application of these products for hydrologic routing. And so we use the Raven hydrologic modeling software to do sort of routing only mode demonstration. And we wanted to try this on a large scale. So we took the Hudson Bay watershed, which is a very large scale, and it's about 40% of Canada. And then when we do routing, we have to generate water that's applied to the routing network. And so we get these forcings or fluxes that move onto each subbasin. And these are derived from the gridded hourly surface runoff and groundwater discharge that Environment Canada predicts with their sort of SVS land surface scheme. So this is about, this is similar or is the essentially operational product that Environment Canada uses. And that's where we get the inputs that we want to drive through our hydrologic routing model. We have to do a spatial overlay of the gridded forcings. This model is a gridded model, so we overlay the grid on our irregular routing network so that we can generate sort of weights for Raven that allows us to map gridded forcings onto a vector-based map. We can directly read in with Raven the original resolution grid forcings in either NetCDF or ASCII format, so that's really convenient. And then the conversion to sub-basin shapes happens within Raven. In Raven, for this demonstration, we'll use the diffusive wave routing mode. We're not doing any in-catchment routing simulation, and then we'll also be simulating lake water levels. We'll just do a 3-year simulation at an hourly time step, and this example simulates 15,000 lakes and 26,000 subbasins. And so we just wanted to show that the software and the methodology works generally. So one slide about Raven. Probably you've heard about it, but if you haven't, it's a Waterloo product that we use. It's a hydrologic modeling framework developed by Dr. James Craig. It's a flexible framework, meaning that you can choose the processes you want to model. You can choose whether it's a lumped or distributed model. You can simulate the full hydrologic cycle, or you can just route surface runoff, which is what we're doing in this example. And this is, again, the first time demonstration of Raven in routing only mode. There's a lot of benefits of using Raven for routing, I think. There's 5 different routing process options that you can use. Analytic diffusive wave is one of them, but you can also use Muskingum, for example. It allows for NetCDF format, which is an efficient file format type. It allows you to do gridded spatial discretization or subbasins, vector-based. You can explicitly model lake levels and lake processes, and it actually supports wetlands and routing of tracers and other contaminants. So looking at the quick results to see that this makes sense, when we run this model across Hudson Bay, we check the results at 15 different gauging stations that have no upstream management impacts. And what we can see here is on this axis is the Nash Sutcliffe efficiency. This is the level of agreement between the simulated flows and the observed flows. Value of 1 is the best. And so these different bars show different scenarios. So the bluest bar is when we simulate all lakes in our routing network, and the yellow bars are when we simulate no lakes in our routing network. And you can see that, especially for some of these basins, it's really important to try to represent lakes because at the default routing configuration and routing parameters, we see an improvement in our quality of modeling results when we actually try to represent lakes explicitly. And if we try to look at why is there a difference between modeling with lakes and modeling without lakes? So this is the improvement of modeling with lakes. There's a definite relationship as the percentage of lake coverage in the watershed increases. We have more and more, there's bigger differences in the performance if we ignore lakes versus not ignore lakes. So that's not too surprising, but that sort of confirms what we would think. This is an example hydrograph at one of the basins. The dashed line is the observed hydrograph over 3 years. And the base scenario is the blue scenario where we use all of our information in our routing network and represent all the lakes and then route through them. And then the light blue is when we do not simulate lakes in this routing network. And you can see what one would expect is that when you don't have lakes holding onto water and delaying the delivery and reducing the peaks, the simulated results are not at all close to the dashed line and the observations. And so the blue line here is much more representative of the actual behavior of the system. And so just an example where we really need to include lakes if we want to predict flows. One quick look at routing efficiency in our routing model application. So Hudson Bay is 40% of Canada, and it turns out that the runtime, if you want to do a typical hydrologic forecast 10 days out at an hourly time step, this model takes 6 or 13 minutes to run depending on the resolution. And the main thing here is just to show that these simulation times are actually reasonable given their serial, and they could be improved drastically if you just parallelize the routing, which is possible. We also don't include recent code optimizations here. So this is basically an old benchmark. So I think if we redid these benchmarks, this would reduce significantly. So the model itself, modeling tens of thousands of lakes, is actually feasible. It's not a computational bottleneck. Now, the last thing I want to talk about is the GIS Lake and River Routing Toolbox. And this toolbox is built so that users can essentially customize the routing product and build it from scratch as you see fit. So this routing toolbox is actually, it's been in the works for a year and a half at least now. I think it's really close to being submitted to environmental modeling and software. The lead author again is Ming Han. But essentially the toolbox gives users the ultimate flexibility to customize which lakes you represent in your network, create larger or smaller routing subbasins, define any point of interest as a subbasin outlet. You can utilize any DEM or lake polygon shapefile that you want. Remember, our routing products that I just talked about are actually all based on Hydrosheds DEMs. And so if you don't like that one in particular, you have a more detailed one, a better resolution DEM, then you can use that in our routing toolbox to produce your own routing network. So a couple other things about that. Why do we need to build a routing toolbox? Hasn't anybody done that? Well, not really. There's this SWAT to Lake routing toolbox that was just published 2 years ago. Unfortunately, this is a toolbox that basically allows users to parameterize one lake at a time within the SWAT model. And so that's not very helpful if you have 100 lakes. You can try to use ArcHydro and ArcGIS, but that's not easy, and it actually does have long processing times. So there's some negatives to this. And there's other limitations too. In both of these approaches, neither of them actually provides all the a priori estimates that you need for geospatial hydrological routing parameters. So we really do need a tool that can be customized. And so we build this tool within the QGIS framework, so it's open source. It depends on a number of Python scripts, and we're working on a GitHub page that will become public soon. But essentially what we're doing with this toolbox is we're trying to be explicit about which lakes get connected to the routing network, which lakes do not get connected to the routing network. And then in the toolbox itself, we're going to be producing networks where you can essentially handle non-connected lakes. One of the things that needs to happen in the toolbox if you start with a new DEM is we need to merge the DEM with the lake polygons. And so here's an example of a DEM with a flow path associated with it. And what happens is these are all flow direction arrows. And when we overlay a lake shape on top of that, then we have to look at the DEM the DEM flow directions under the lake. All of these red arrows here show the DEM going in the wrong direction. Any flows on this DEM cell actually flow outside of the boundary of the lake and don't go to the outlet of the lake. So what we had to do in the toolbox is come up with a very efficient way to correct all of these drainage directions that don't quite jive with the lake polygon or the fact that there's a lake on top of that DEM. And so that's another function of the toolbox, is to do this correction in a very efficient way. Other things the toolbox can do, it provides multiple options to define what case study you want to measure. You can specify the outlet point to start working on the delineation. You can use existing routing product like hydrobasins to do that. The other nice thing about the toolbox is it actually generates Raven input files directly. So there's two options for the routing toolbox. You can create shapefiles essentially that has all of the routing attributes saved in them, but you can also automatically create all of the Raven model input files so you can immediately do routing in Raven after this processing. Another good thing within Raven is, and actually just in general, is if you supply like a gridded forcing shapefile, then the software will do an overlay of the forcing grid and this should say the subbasin grid essentially, so that the model you can easily map between forced surface runoff fields on a grid to your vector-based routing network. The last thing I think worth noting here is that we allow people to essentially start with the left figure here is a complicated routing network, let's say, and the toolbox allows people to say things like, you know, I don't really need to model this as 3 different subbasins, and so you can basically merge subbasins together on in whatever way you want and simplify the network from a more complex network. So this would be more efficient to run and maybe better suits your needs. And this part of the toolbox can actually be done without doing any DEM processing, and so it's actually super efficient to be operating this way. If you're interested in the toolbox, I would say you can email Ming. We're close to putting it up on the GitHub, so I think we'll be able to share it with a few people, but certainly the toolbox itself will be freely available once our paper is actually submitted. Just want to acknowledge the support that we've had over the last 3 years with this project. The support started with and has been primarily from Global Water Futures and specifically the Lake Futures Project. We've got current ongoing support for our routing work through an Environment Canada and Climate Change GNC grant that's to James Craig and myself. And I should also note that we use SharkNet and Compute Canada to do all of these computationally intensive simulations. And the last thing is to thank Nandita for supporting this work, as well as Vincent Fortin and Al Piccinero, both of Environment Canada and Climate Change, for continuing to support our efforts in this area. I greatly appreciate that. So with that, I think that's the end. So I'm supposed to have a slide that says thank you. So I think I'll stop talking. I'll be happy to take any questions. Kirsten, should I stop sharing or what should I do here?
You could switch back to our other presentation. We've got a slide for Q&A.
Okay.
But thank you, Bryan, for that presentation. So we'll now move to the Q&A. And as Nancy said in the chat, if you could please post your questions to the Q&A box. And if there's anything else that you'd like to discuss, you can use the chat box for that.
Can you see that now?
Yep, that looks good.
Okay.
So the first question we have, Bryan, is, did you compare the performance of hydrological forecast between the products, including lake and the product that doesn't take lakes into account?
No, we didn't do any comparisons in forecasting mode. So we just went historical data and went back in time and looked at in just historical mode, not in forecasting mode.
Great, thanks. Next, could you provide some examples of how outcomes from this model would be different between using vector versus using gridded routing?
We're trying to do a lot of that with Environment Canada right now. One of the challenges is that I don't have any results handy right now. One of the challenges is it's to include an irregular shaped lake into a finely gridded routing network requires some very specific and very careful work, and sometimes not even possible. And so even getting a network that includes all the lakes in a gridded network is an incredible amount of work. And so that comparison is actually difficult to do. But we've showed some work with Environment Canada, and I'd be happy to talk to whoever asked this question later and dig it up. But we do have some examples where we show that a gridded approach is less not quite as good as the subwatershed-based approach or the vector approach. But the other thing is that, you know, the vector-based approach is much more scalable and much faster. We don't have to route, you know, 1 kilometer squared subbasins on average. We can route larger subbasins and still be accurate, whereas it's not really possible to increase the resolution of the gridded network, especially if you're trying to respect lakes that are on the order of the same size of the grid. So there's a lot of challenges there, but there's a lot of benefits that we've shared with Environment Canada, and we continue to try to demonstrate that.
Thanks. Our next question is, how would somebody add regulation plans to modify the lake outputs?
Yeah, so that would be one of those case study specific things. If you're doing if you're building a hydrologic model of an area, and you know that there's, you know, 3 of 100 lakes are actually managed reservoirs, and you have specific information about how those managed reservoirs are controlled, you know the outlet structure, then you actually need a routing model that can represent the management of that reservoir. Raven does allow for that. Raven has capabilities to include management strategies and various reservoir control strategies, rule curves, and whatnot. We don't show that here, but that's not a piece of information that's currently in the routing products itself. But hopefully the flag that says it's a regulated lake would actually cause somebody to not assume it behaves as a broad-crested weir, and do some more case study specific investigation to figure out how to represent or how to simulate the outflows of that lake in particular.
Great. Our next question is about using examples from different regions in Canada. So while you shared results for a select number of WSC stations in the Hudson Bay basin, yep, people would be interested to know how the system performed over other areas, particularly the prairie pothole regions. And will future results be made available?
Yeah, so we are moving in that direction, and so what I'm involved with Julie May in another project in Lake Futures called the integrated model. Why can't I think of the name? The model intercomparison study for the Nelson River. And what we're trying to do, what my role in that project is trying to do, is to use this routing framework to be able to route people's model predictions in the same way. And so as part of that project, we'll be applying it across the Nelson, and we'll be figuring out how the products do in terms of representing the prairie pothole regions, and then how the combined sort of hydrologic predictions and then the routing in the routing model that we apply actually work. So we will be doing those tests, but we haven't done, you know, large scale tests to show that show the quality of the routed results, because of course in any application of our products or of our routing framework with Raven, we need to generate the surface runoff estimates in every subbasin. And that's what a standard hydrologic model would generate. They would generate those estimates. And so the quality of any predictions from our routing model is a function of the surface runoff that's produced by a different model, and then the quality of the routing model itself that we would be applying. So that was a bit of a long answer, but hopefully it was clear.
Great, thanks. So next is, do you have thoughts on how we can most appropriately discuss the uncertainty in model outcomes? How should decision makers interpret the different confidence levels in these predictions?
Well, that's a big question. That's a big question. We do not, so in the context of the work that we're doing, everything was viewed from a deterministic lens. We We didn't produce uncertainty estimates on the network topology or the routing model parameters. But I do think that, my view on uncertainty and modeling is that the first step in considering model prediction uncertainty is to build a deterministic model. That you have to do that. And then once you build a deterministic model, you step back and you look at all the model inputs you have, and you start to say which of those are probabilistic or unknown, and you then plan your next analysis to start to describe the uncertainty in those model predictions as a function of the uncertainty in the inputs. And so every sort of uncertainty-based study starts with deterministic-based model predictions, and then you need to do some more advanced work to build the uncertainty bounds in your predictions. But in general, ideally in any study, you would try to be describing the uncertainty. But that's usually twice as much or more work than building deterministic models. So it's a challenge, but I think it's super important.
Great, thanks. Next, there's a comment in the chat box that maybe you might be able to speak to. So this is from Adrian Ether, who has developed a simplified aquatic mercury model for lakes and rivers that was applied by Environment Canada to over 200 lakes to create a predictive map of mercury risk for the State of Science report. They're thinking components of that might fit in with some of your work. Do you have any comments or want to speak to that at all?
Yeah, it does. I mean, it depends if the 200 lakes are treated as an independent model, or if they're a series of connected lakes that ultimately are part of the same watershed, where the mercury output from one lake flows into into another lake downstream and whatnot. Then I think there's definite overlaps, and in terms of how this work would interface with that kind of project, I guess if you were going to start a project like that and you knew the area that you were interested in, and you had mercury measurements from all 200 lakes, then you could actually start with our product to try to discretize the region and discretize it appropriately, and have a routing network to know where flows go and everything like that. The Raven model itself, developed by Dr. Craig, is undergoing it's in constant development mode, and so right now it does support tracer work, and so it would be and it's being developed to do some non-conservative transport as well. So I don't think Raven is too far away from supporting some of the contaminant transport modeling that would be associated with moving around in rivers, but that's certainly on the horizon. So I hope that answers the chat question a little bit. I'm happy to talk to whoever made the comment offline if they wish.
Great. One more question. Do you know if there are governments, consultants, or other agencies using your products? And do you have a sense of how they're using them?
I don't right now. I guess if Ming Han is listening, which I hope he is, he might be able to tell you some statistics about who's downloading the products. I really don't have a sense for that, but I really think it's useful, and I think that for anybody who hasn't built or who is building, a subwatershed-based hydrologic model or water quality model in their watershed, I think this is a great starting point to use to consider what kind of discretizations could be used. So I really do think it's very useful as a starting point. It doesn't, instead of you having to do DEM processing and arbitrary subbasin delineation. But I don't have a good handle on the user base for this. I know a lot of people anecdotally have said, this is great, I need to use this. But yeah.
Great. So maybe as one last question as a follow-up to that, Can organizations with existing hydrological models improve their systems with your new tools and routing strategies? And if they wanted to do that, how would you suggest they go about doing that? I know there was a link that you had shared earlier, but do you have any other suggestions?
Yes. So I would say, first of all, email me or email Ming, both of us, is the how you would go about that. But what we're trying to do with Raven as a routing tool is we're trying to make it be usable so that it can take any fields, any fluxes of surface runoff that a different model produces, and we can route it through one of these networks. So if your model is, if you're not happy with the way that your model simulates lakes, or if your model doesn't simulate lakes, but you'd like to try to consider the influence of lakes, then we could take your essentially a spatiotemporal time series of the fluxes of surface runoff and groundwater that your model produces at either the gridded level or the subbasin level, and we can easily map that onto one of these product polygons, and then Raven will do the simulation on perhaps a more complicated routing network. So I think that this is definitely a thing that can be done. And that's really what we're trying to do in the model intercomparison project. We're trying to set up the, we're trying to educate people and help people actually do that with models that they're interested in. As part of the work with Environment Canada, we're looking at streamlining the routing, the channel and lake routing that's being done in mesh. So that's an example of that.
Great. So that'll be the last of our questions for today. So thanks, Bryan, for answering all of those. And thanks to everyone for participating. We hope our discussion has been insightful. So we'd like to end our session today with one last poll. And this is, did you learn something that will help you inform your work moving forward? So yes or no, or maybe you're still thinking about it and not sure yet.
Let's see if everybody liked my talk.
We'll give you a few moments to respond.
I should say, as people are responding, so I wasn't sure how this was going to be run, so I don't, we can't have an actual conversation with anybody on the call, but I'll be online for the next hour. So if people drop me an email, btolson@uwaterloo.ca, we can arrange a quick call in the next hour to follow up immediately on anything that you wanted to talk about or anything you want to chat about as a result of the talk. So
great, that is a great opportunity for folks, Bryan.
Okay.
And good news, most people, 79% did learn something, so that is very good.
Awesome.
So just wanted to let you know that we also have 2 more webinars upcoming in our September series. So the first is next week. Elaine Ho will be presenting a new approach and lessons learned, how co-creation and shared space and diversity can improve water monitoring design. And then the week following that, September 23rd, we have Nandita Basu sharing research on sustainable urbanscapes, nutrient cycling in the Greater Toronto area. Registration for both of those is now open, and we can point you to the Lake Futures website for that. We will also be sending you a follow-up email that will have a link to the recording of this webinar. We will also have a brief survey directly following this webinar that we'd appreciate if you could fill out. That would help us improve for future webinars in this series. We're also doing 1-page brief summaries of all the webinars in this series. So if you missed one and want a quick glimpse of what it was like, you can stay tuned for those that will be published on our website soon. Lastly, I would like to thank our speaker, Bryan Tolson, today for your insightful presentation. I'd also like to thank my colleague, Nancy Gaucher, for her help in organizing the series and for producing behind the scenes today. And finally, thank you for joining us, and we hope to see you again soon.
Thanks, everybody.